Precalc chapter 4.2, day 2. First up, we're going to talk about arc length. Now, this arc length idea should look very familiar. It's just rearranged because you guys were introduced to these exact same letters, almost the exact same formula. It's the same formula, just rearranged. When we talked about what a radian was. A radian was theta equals s over r, arc length divided by the radius. And so to get the arc length from there, they said, hey, if you know the radius and you know the amount of degrees in radians of your arc, you now can find your arc length. And so arc length is equal to r times theta. Now, of course, there's going to be some modifications of this, and I have it down here, is that, well, sometimes they give you the question, and you're talking about degrees. The easiest thing to do is just convert it back, or convert it from degrees to radians, which is the degrees times pi over 180. And if you kind of look in here, I get pi right there, 180. So you are multiplying the extra stuff, the degrees, by pi over 180, which converts it to radians, and then you can multiply it to r. So it does do the degree to radian switcheroo, so that therefore the formula does work. So the first problem, and it says it wants it to the nearest tenth, is pretty straightforward because it already gives you the radians, and it gives you a radius. Don't be surprised if the book or a problem says, hey, I've got pi radians, but the diameter is 26. So sure, you could use pi, but you don't get to use 26. You need to use what? We're not using the diameter. We're using the radius. So if the radius is 26, the diameter is 26, the radius would be 13. So make sure that you are using the right things for the problem. So this is 2 pi over 3. That's your radians there. And so if your radians are 2 pi over 3, so 2 pi over 3, times that by 2. That is s. Because s equals theta times r, or r times theta. So when you multiply, that's just multiplying fractions. What do you get? You get 4 pi over 3. 4 pi over 3 meters of all things, because we are talking about a length. The radius was 2 meters. Now this is the exact value. We're not looking for the exact value. We're actually looking for the approximation to the tenth, the decimal. So you have to take your calculator out and do 4 times pi times, or 4 times pi divided by 3. Now I can pretty much say we could probably kind of estimate the value. Pi itself is 3.14. So if I divide pi by 3, it should be just over 1. And something just over 1 times 4 is about just over 4, yeah? So what's our answer? Actually, take a calculator. 1 decimal place, tenths. Ends up being 4.2 meters. Cool?
It's so tiny. Can we make that a little bigger?
Put it on your computer.
The second one is in degrees. I don't want degrees, so just take it, switch it to radians. So I can take the 135 degrees, right? Multiply it by the change. How do I change something from degrees to radians again?
Do the 180.
Over pi 1.
Pi.
Google Maps.
Which one goes on the top, which one goes on the bottom now?
180.
180 goes on the bottom because the degrees have to cancel and the radians get to go on top. So we will cancel out the degrees. Now, watch this. I have now, without actually doing the work, have switched from degrees to radians. All of this will and has now become a radian measure. Yes? That will stand for theta right there. So all I have to do with this answer is take that thing and multiply it by 0.5, because all of that times a half will now give me the arc length. Question?
It's supposed to be radical.
Oh, okay.
Rad. Yep. Radians.
Looks like red.
Yeah, it said,
So you take your calculator, multiply the 135 times pi, divide it by 180, multiply it by 0.5, and you end up with a value of what to one decimal place?
1.2.
1.2, in this case, feet.
Feet, yeah.
So if it's in radians, multiply by the radius. If it's in degrees, switch it to radians, then multiply by the radius. The middle piece, the second thing for today, is talking about linear speed and angular speed. This is something we did cover last year. And so we're not going to probably go in as in depth as we did last year with this one, like switching between the two. We'll just kind of restart them. But linear speed, guys, according to the book, says it's the rate at which an object moves along a circular path. Your tire does rotate. It goes in circles, but at any given point, if you set your tire on the ground and let it roll, it will cover a linear distance over a time. And so your tire at the end is spinning around, finding a distance. And that distance that you're going to travel over an hour or a minute can be feet per second, miles per hour, meters per second, things like that. That is linear speed. The fact that you're spinning a tire on a fixed point, we say the tire rotates, has revolutions per minute. So your tire may rotate twice in a minute. But if you have a very large tire, that rotation could be an actual pretty good speed. But if you have a smaller tire on their car, 2 revolutions may not go as far, because you have less distance to travel with that larger or smaller tire. Okay? And so we have the ability to find a linear speed and then an angular speed. Linear speed, like I was saying, is the distance the tire travels on the outside over a given time. Well, the distance a circle travels, or a distance around a circle, is s. And s is the arc length. So the arc length of a circle divided by time. Now here's the interesting part about the arc length of a circle, or of a tire. Your tire can go around many, 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 many times. And so therefore, 1 revolution would be the tire going around once, so you'd be the circumference once. But if I go around twice, that's 2 circumferences, circumferenci, I don't know how you say that. And then so on. So the more times your tire spins around, the further your tire will go, the higher the linear speed will be in a given time. If you talk about angular speed, which is the lowercase omega, the W, you just take the amount of radians you travel divided by the time. So if I make 1 revolution, it's 2 pi. If I make 2 revolutions, it's 4 pi. 10 revolutions, 20 pi. Over a given time. Is it a minute? Is it a second? And an hour? Obviously, the more rotations per given time, the faster it goes. Does that make sense? So the problem is like, how can we apply this? When does this kind of make sense? It's going to make sense on the next slide. Are we ready for that? So to do this problem, we're going to find the angular and linear speeds. We're going to be given the information that a certain DVD, I don't know if all of them are or not, but a DVD is 120 millimeters in diameter. We'll need that for part B, not for part A. Part A, or the first part, asks us to find the angular speed of the DVD in radians per second if the disk rotates at a rate of 3.5 revolutions per second. Remember, angular speed, though, angular speed, the omega, is equal to theta over time. But theta, guys, is the amount of radians that passes in the given time. It's making 3.5 revolutions. And if every revolution was how many radians again? 2 pi. Wouldn't it be really easy to say, hey, if I take 3.5 and multiply it by 2 pi, it'll tell me exactly how many radians have just passed? There's your radians. Over the given time, what's your time? 1 second. And what's 3.5 times 2 pi? To make it easy, just stick with pi's, 7 pi. Radians per second. That's your angular speed. For the most part, for us, we don't recognize angular speed. We like linear speed. If I said, hey, it's going 5 miles an hour, you might get an idea what that is. If I said 25 miles an hour, you would know what that is. You've driven in a car. You've gone 25 miles an hour. Okay? 7 pi radians per second, or roughly 22 radians per second. So if you knew what a radian was, you'd go 22 of them every second. Remember, a circle has 6. That's 3.5 times around a circle every second. That's moving pretty fast, actually. Now, part B asks us, hey, the DVD player is starting to overheat. It begins to slow down. We're only at 3 revolutions per second now. Find the disk's linear speed in meters per minute. Well, first of all, everything we know about this is not in meters per minute. It's in something else. We definitely know it's per second. But what's the size? The size is in, the only other measurement we have is millimeters above. So we're going to first have to find this answer in millimeters per second, and then we're going to use a little dimensional analysis, convert this thing over to meters per minute. Something that might be more useful for us. Okay, wait, linear speed, isn't that V? V equals S over time? Arc length over time? Wait a minute. I don't know what arc length is again. There's a formula for that. What was arc length?
S equals R.
Theta.
R theta. So if I know the radius and I multiply it by the number of radians that passes, I'll know the arc length, and then I know the time. Time is 1 second, right? So that's all over 1 second. What's the radius of this DVD?
60 millimeters.
It's 60 millimeters.
Because it's 20 in the diameter.
Diameter says 120. Half of 120 is 60. So I got 60 millimeters. That was my radius. What is the amount of angle it's traveling? How many radians?
Well, 3 full rotations.
3 full rotations.
6
So it'll be 3 times 2 pi,
pi, which is 6 pi.
which is going to be 6 pi. Now, okay, so we do this, right? This would become 60 times 3 times 2 pi.
Which is
360?
360 pi millimeters per second. Here, I don't like that slanted line there. So per second, because I'm going to use dimensional analysis to cancel my units. So does anybody really understand what it means to go 360 pi? Well, first of all, you can basically multiply by 3 somewhere over 1,000 millimeters per second. Is that a lot? Is that not a lot?
I don't think it's a lot.
I don't know. But I think if I convert it to meters per minute or miles per hour, it might give us a better idea, right? So how can I use dimensional analysis to get rid of seconds?
Oh, to get rid of seconds, you do 60.
60 seconds over
You
1
do 3,600.
minute? No, we're not going to hours. We're going to go to minutes first because our problem wants us to go in minutes, meters per minute.
Okay.
We'll eventually convert it over because I don't know if this is going to be good enough either.
Yeah.
But okay, so seconds should cancel. Now we got to go from millimeters to meters. So millimeters definitely need to go on the bottom. How many millimeters?
1,000.
1,000. Metric system's so nice, isn't it?
Yeah.
So 1 meter to 1,000 millimeters. So those get out of there. And so now I need to take my calculator, take 360, times pi, times 60, and then divide all that by 1,000. How fast is this thing going? If I was able to put the DVD player, take the shroud off of it, and put it on the ground, and let it roll as far as it can in 1 minute, how far would this DVD roll?
Did you actually get that?
Would we get
I got 67.
Yeah, don't say.
67.85,
8.
I think it was, or 8?
5.
85
Yeah.
meters per minute. 67.85 meters. Well, think of this. I think a meter is bigger than a yard by about 3 inches. So therefore, that's over 67 yards in a minute.
Oh, wow.
Now, you guys all have computers. Look it up. What's 67.85 meters per minute? What is that as miles per hour? I'll pause the video so we can...
Wait, what'd you say?
So we found out it's actually only 2.5 miles per hour. Seems like it should be a lot more, but it's not. At least not mathematically. We could do all the dimensional analysis to get there. We just let the computer do it for us. Any questions on this, guys? Take it, use the formulas correctly, everything's going to be fine. And then we're going to end on a better note, because that stuff kind of gets a little interesting at times. End at a better note with the idea of area of a sector. It looks difficult. I'm going to show you guys what it really actually means. Break it down just a little bit. The area of a sector, guys, a sector is just like the piece of pie. The blue section here is called a sector. It's where you have an area bounded by 2 radii and its intercepting arc. And so, if I wanted to find the area of something, I just have to find out how much of it is the circle is being used and multiply it by its total area. Guys, think of this. If I said that a particular cake had 1,000 calories in it, and I just told you I ate half the cake, how many calories did I eat? 500 calories, okay? So, it's the same idea. If you want to know how much an area is worth, you figure out the percentage of that area represents, and then you multiply that to the total area of the object. So if I'm using pi radians, well, that's pi out of 2 pi radians, that's half. So therefore I'm using half of the area, which is pi r squared. So this formula right here is when you are in radians. It's 1/2 r squared times theta. You can remember that. Or you can use the fact that I can say if I'm in radians, I will divide whatever I'm given for radians by 2 pi. So again, if I'm in pi, if I go pi, pi divided by 2 pi is 1/2. I'm using half. and I just multiply that by pi r squared. This thing right here is allowing me to set up how much, aka percentage, decimal, whatever you want to call it, of the circle I'm using, and I happen to choose the area. This same idea actually can be used for arc length. If I know how much of the circle I'm using, that can multiply that percentage to the circumference, pi r squared, or 2 pi r. And that'll tell me how much or how long that piece of crust will be. Now, if I was, say, in degrees, well then I would just take the amount of degrees divided by 360 and then multiply that by pi r squared. Now here's the really cool thing. This one allows me to transfer from degrees actually into radians. You can make this switch to get to this formula. But look here, wouldn't pi's just cancel out? One's on top, one's on bottom? And then that would leave me with 1/2, bless you, a theta and an r squared. And that's exactly what the formula says. So it does not matter. Now, if I was just thinking of this on my own and didn't have a formula, I probably would choose one of the two that I just created here in the purple. But if you have access to the formula and you know that you're in degrees or radians already, radians, then hey, if you're given the fact that theta is 3/4 pi and you have a radius of 1.5, just multiply them together. So I can just say, hey, the area is equal to 1/2. Now notice that I have to do 1/2 r squared, and r right now is 1.5. How many people know what 1.5 squared is right off the top of their head?
2.25.
It is 2.25.
Yeah.
But not everybody just said that right now. So, but I think everybody would understand that 1.5 should be 3/2. Now, if I asked everybody right now, how do you square a fraction? Everybody should be saying, square the top and then bottom. So guess what? I'm going to switch that to a fraction so that I can do this in my head. And then I'm going to multiply that by the amount of radians. Well, when I square 3/2, I get 9/4.
Yeah.
And when I multiply fractions, I just multiply across all of the top, and I multiply across all of the bottom. What's 1 times 9 times 3 pi?
Is 27 pi.
27 pi over 2 times 4 times 4.
32.
32. And we're in feet, and since we're talking about area, it'd be feet squared. That's the exact answer. If I wanted an approximation, I just put that on a calculator and go to 1 or 2 decimal places. Try to think of ways and how these are connected, because a lot of this stuff is super connected. Now, again, I can take 50 degrees in part B and just completely switch it over and then put in the rest of the formula. Or I could use that second purple formula that says, hey, I'm using 50 out of 360 degrees, and I'm going to multiply that by pi times 6 squared, pi r squared. And if I put this on a calculator, I'm going to end up with meters squared. Six squared is 18. I think 36, sorry, yeah, my bad. I don't know why, I don't even know where 18 came from. I know I could cancel out zeros. So therefore I'd have 5 over 36 pi times 36. Wait a minute, the 36's can. So I'm left with 5 pi meters squared. And again, I could put that on my calculator. 5 times 3 is about 15. So it's probably around 16 because of the change that gets left over. 15.7 meters squared. Okay? So it's not too bad. You guys got to think about these things a little bit. Notice that there is a huge connection between arc length, how to find areas, radians, sorry, and then the areas and the arc length as in the way you can find them. Think of it as percentage of it and multiply it by the formula for the distance around a circle or the area of a circle. Homework, that's day 1. How about day 2? Still page 238. Let's do 27, 28, 34, 35, 41 through 44. Have a fantastic day.